Lowell, Massachusetts became a center of the textile industry in the early 19th century, when it harnessed the power of a 30-foot drop in the nearby Merrimack River to run the textile mills. Tamed into a system of locks and canals, the falling water ran under the mill buildings and turned the blades of huge turbines, which powered the mill machinery. When the industry moved south, the mills and turbines were abandoned. But today, we are rebuilding one of the 5 1901 horizontal turbines at the Appleton mills in Lowell, with the goal of generating electricity at a profit. David Wright, the engineer in charge of the turbine renovation, explains how the system works.
When the canal is drained, we can see the openings to the waterways which supply the water to the turbines. This tunnel is the conduit which supplies the water to the turbines. Presently it is empty because the wooden head gates at the entrance to the tunnel are closed. When the head gates are open, this tunnel will fill with water, filling this chamber with tons of water. That water will drop with a tremendous force through the turbines, 13 feet, and enters the turbine through these guide vanes. Behind these guide vanes are the water wheels. There are 2 on this installation. The water wheels are similar to what you think of when you're thinking of a grist mill, but they are a much more advanced technology. They're cast iron, and they are configured somewhat like a propeller. We'll be able to see that from the outside later. The mechanism which controls the amount of water, therefore the amount of power, is a large cylinder inside these guide vanes. When the cylinder is drawn back, water can flow into the turbine These 2 water wheels are mounted on a large pounded shaft supported by a wooden bearing in the center of this housing. The large shaft is the main transmission device transmitting power through the large flywheel at this end of the turbine. This is the sheave, or pulley, or flywheel, connected by the shaft that runs through the pressure case to the turbine. The sheave will be connected to a leather belt to the electric generator, and when it turns, the belt spins the rotor of the generator. Much of this room is dedicated to the governor, which controls the amount of water to the turbines, thus the amount of electricity produced. This is the pressure case. On the other side of this wall sits the turbine. This gate shaft is connected to the cylinder gates, which we saw before. The gate shaft is connected by these bevel gears and these pulleys and cables to the governor. The governor is the most complex part of the system, since it controls the speed of the turbine by controlling the opening of the gates. It can be operated manually, like this, but the governor is also designed to operate without supervision, automatically controlling cylinder gate openings, thus turbine speed.
get the turbine into operating shape, one major job we have is to fix the turbine casing. These steel walls contain the force of the water as it rushes toward the turbine. For large areas, it's simply rusted out. Ed, the job welder, has to cut away the rotted sections before welding and bolting the new steel plates in place. The old turbine needs many mechanical repairs before it can run again. This coupling is a link between the cylinder gates and the governor. It's slipping, so the cylinder gates can't be adjusted properly. To realign them, we first make sure that the gates are in place by positioning them manually with the governor wheel. There are two couplings, in fact, one for each set of cylinder gates at each end of the turbine. To make sure the gates would operate evenly, we go from one to the other and count the number of teeth showing on the rack to measure the distance the gate is opening. Finally, we find we have to go down into the turbine casing to loosen and reposition one gate arm. Then we can hammer it into place. With everything positioned correctly, we are ready to drill a new hole in the coupling. We tap threads into the hole, and secure the coupling with a new bolt. Meanwhile, Ed is winching up a new sheet of metal to replace the rotted out parts he'd cut away. When it's in place, he trims it to the exact size with a torch. Then he pounds it even and clamps it. And finally, he is prepared to weld the seams shut and watertight. Seth is working in the tiny bearing chamber between the two turbines. To get there, he first drops into the main pressure case through a manhole in the top, and then lowers himself into the space between the turbines. In this chamber, Seth is chipping away the layers of crust that have accumulated since the turbine was abandoned in the 1940s. Everything must be cleaned and taken apart to inspect its condition. Our first task is to remove the metal casing from the bearing which surrounds and supports the central shaft. We burn the old bolts, then cool them with water, in order to loosen them so they can be wrenched off. With the upper half of the bearing case removed, the top part of the wooden bearing can be probed for signs of rotting. Now the top part of the wooden bearing is lifted out of the chamber, and we can see the metal shaft, no longer smoothed but pitted and gouged from years of use. The next task is to smooth down the pits and gouges in the shaft. First, we sand the shaft directly. Then we mix up a batch of red hand, an epoxy compound, which is applied in a thin coat the length of the shaft.